Hi, welcome back. We're going to look at 310 because that's where we left off. Okay, so let's look at the question really quickly. It says, let X represent the outcome when a fair-sided die is rolled. This is a random variable. So we don't really know if it's normal, but we do know that it's random, so we don't know the distribution. And mu is 3.5 and the standard deviation for a single roll is 1.71. If we use the same die and we roll it 100 times, what's the approximate probability that the total score is at least 3.75? Okay, so to think about this question, we have to do a little bit of thinking. We see in the back that the answer is C, but some of us got C just by guessing and some of us got a different answer. Okay, so let's take a look. Well, using transformation, this is definitely transformation. Our average amount we'd get if we rolled it once is 3.5, because we're going to get 1, 2, 3, 4, 5, 6. And I actually could tell you how to calculate that as well if you're interested. But so if you roll it once, you're going to get a typical score of 3.5. That's your average. You're going to get higher numbers and lower numbers, but your typical score would be 3.5. So if you rolled it 100 times, that would be your mu of total. Now this is the jump. We want to be able to multiply by 100, but we fall in the same trap again. We can only add variances. Eek. So we got to be really careful here, and it feels like we can add these. You know, I wanted to just add these, but oops, I can't. So let's think about this. I rolled it 100 times, and multiplication really is repeated addition, isn't it? It's 3.5 for the first roll, and then 3.5 for the second, and then 3.5 for the third, and oops, who cares? I'm just going to multiply by 100. I'm not going to add 3.5 100 times. But we do have to add when we do variances, and we'll see why that matters. Okay, so when we take this, the standard deviation of the total, and we square it, this will be the variance of the total, because variance is standard deviation squared. So when we take the standard deviation of the first one, plus the standard deviation of the second roll, plus the standard deviation of the third roll, plus the standard deviation of the fourth roll, and we square each one separate, right? So we're really adding the variance of the first, the variance of the second, the variance of the third. We keep doing that. We're going to do that 100 times. And notice how the 100 fits in front of the square. That's 100 times we're going to add that number. So now when I find the standard deviation, which is, this is the standard deviation of the total, notice I'm going to have to take the square root of this, and I end up getting the square root of 100 times the square root of a square, which is just that number. And the square root of 100 is 10, and so that should make sense why I got 17.1. Okay? Now that I know the standard deviation of if I did this 350 times, we can use normal. Now, even though, because it's such a large number, the distribution of a random variable will converge with normality, and we could use normal CDF to calculate that number, and that is our answer, C. There it is. Okay, next question. It states that we have an agricultural station, and we are interested in 6 different varieties of corn. So I actually am being a little bit aggressive. I have 6 different varieties. So I have 6 different types of seeds that I'm interested in finding something about, okay? And it says I have 4 fields available, and they happen to be in different parts of the county. So I just kind of drew a picture, North County, South County, West County, East County. 4 different parts of the county, I have fields, and I divided them into 6 sections because I got 6 seeds I'm interested in testing out. So the answer to this one is B. And so let's take a look. There's some sneaky maybe questions that look good but not good enough. This is a randomized block design with fields as the blocks and the seed type as the treatment. So when we think of this, we have to block when we know for sure that things will be different in these situations. So the classic idea of blocking is blocking men and women. That's when we know that they're going to have, let's say this was a drug, and we know that, or a prescription, we know that the way a man might react to medicine might be different than a woman. So we want to block that. We want to separate things we know might be slightly different. And that's really what we've done for these fields. So this is blocking. And again, what we're doing to these fields is planting seeds in them. So that is the treatment itself. Okay, and that's why B is the best answer. Okay, C. So I put on here a little bit of notes. I also just said read the question. So it says the correlation between the heights of fathers and the heights of their sons is only 0.52. That sounds a little low for me, but okay. It does make sense that fathers sometimes have more than one son, and those sons are different heights. So it does make sense that if I know the father's height in inches, I'm not going to perfectly be able to predict the son, but there may be some amount of correlation there, and that's what an R value of 0.52 says. Okay, now think contextually. If we changed the father's height and listed it in feet, maybe as a decimal, and then we list this in feet, then the distance that these numbers are away from the line of best fit would not change at all. The only thing that would change are the two labels of the graph. So that should match C. It is unchanged. R is unchanged when we convert, and hopefully you convert both. R is unchanged when we convert both X and Y by the same units. Okay, hopefully this would make sense. Another typical example would be when you convert, if these two were Celsius or something, and then we convert them to Fahrenheit. All right, next question. 13.3, it says a random sample of New Yorkers voted Republican, 88 Republican, a random sample of 300 voted 141 Republican. Which of the following represents the confidence interval? So we find that this one matches what we're looking for. They wanted the true difference in proportion of Republican. So here's our proportion of Republican in group 1, and that's the complement of that. See how those two numbers would add up to 1? And this is in of our group 1. So this is the proportion of Republican in group 1, and this is the proportion of Republican in group 2, and this is the number of people in group 2. Okay? So another thing to look for, all of the answers had this critical value, but that sometimes is a way to quickly find your answer. And then this is the difference between the two. So you every choice had this as an example, so you pretty much knew that was going to be set up there. I think most of you got this right, so we'll move to the next one. 3.14 says, which of the following is not a property of the binomial setting? Which of the following is not? Okay. So actually each one of these meets the requirements for the binomial setting, and one of them actually meets the alternate requirement for a geometric setting. And that's our answer right here. So the way we remember the requirements of the binomial setting is to remember the abbreviation BINS, bins. D is actually the T in bits, which is how we remember the geometric. So let's take a look at our notes here. So on this question, we're looking for what piece is not binomial. So we see part A talks about the outcome of the trials are independent. Okay, so we're not going to pick A because we're picking the one that is not binomial. Okay. Number B says the chance process consisted of a fixed number. Okay, fixed number. That is a component of binomial. B-I-N-S, that's what the N stands for, a fixed number. So we can't pick B because we need that as part of our test. C says the probability of success is the same for each trial. We need that. So part C is the component we need for the S. And D is the one we know is our answer because it is the component that we need for a geometrical distribution, not a binomial one. So that's the one we know is the right answer. But let's just check out E. E is the component that each trial is either a success or failure. And so that's just two outcomes, success and failure. So this idea of two outcomes, success and failure, is binomial because binomial means two. Now, what is geometric? It's exactly the same thing, except instead of a fixed number, we keep going until we get our first success, and that's a geometric. Thanks for watching the video. Feel free to keep watching for questions that you've missed.